one more thing I'll need, but we'll write it right away. So yesterday we discussed this effective theory that we built to compute the decay of a neutral D meson into a D meson and a phi minus. And the exact process is not even that important. But what was nice in this particular case is that there are a lot of work flavor changes, so there are not many operators one can write down that does do this. It was only two operators, these two operators O1 and O2. Then we had an effective Lagrangian. This still contains QCD, but the W boson we integrated out, and as a result we have these effective operators times some coefficient which contain the CKM matrix elements, and then coefficient C1 and C2, which we computed or at least read off the result from a one loop computation. So we're in pretty good shape. We know these coefficients even at the one loop level. And now we can use this Lagrangian if we want to compute this process. If we do this, then basically what we have, some I equals 1 to 2, which we'll just have to compute these matrix elements of these two operators. Times the Wilson coefficients. G and C I mu times this. What was interesting is that this mu dependence is arose in the process of renormalization. We did these loop computations both in the effective theory and the full theory. We looked at the difference and we read off the values, and you see that these values depend on mu. If you compute this matrix element, Mi, easier expectation value OI, this will also depend on this mu. Now this mu was introduced in the process of renormalization, but this mu dependence, this mu is just an unphysical scale, so it has to go away. So the slightly schematic, of course I have to square and do phase, I should maybe write the amplitude for this thing here. So this mu dependence has to cancel out. And we can in principle choose whatever value of mu you want to choose. So if you want, you could make a suggestion for what value of mu would be good here. There are only wrong choices, so whatever you do will be okay. Looking at these coefficients, I think it would be good to choose the mu squared roughly equal to mw squared, because then these logs go away. That would be good. Then these coefficients have a nice perturbative expansion. But these low energy matrix elements, they only know about low energy scales. So the typical scales in here are p-quark mass, John quark mass, etc. So if you do this, then you will have large logarithms in these low energy matrix elements. So choosing a high scale is a bad idea, or is a good idea for the Wilson coefficients, but a bad idea for the matrix elements. Choosing a low scale, sort of the natural scale for this low energy matrix element, is a great idea for the low energy matrix elements. But then if we choose mu equals MB, for example, then we have the large one. Now the fact that the product of these things is independent of mu can be used to derive an equation which gives us this mu dependence to higher orders. And in this way, we'll be able to resum these logarithms. And so that is the topic, the first hour today, this resumation, and then in the second hour, we'll switch to modern effective fields.
Sorry. In my notes from yesterday, I remember this 11/6 you mentioned was scheme dependent. How should one think of that?
What this means is, so if you choose different schemes, you'll get a different answer here, but you will have to compute the matrix element in the same scheme, and then also the scheme dependence should go away. Another interesting thing I can mention here, after the long discussion yesterday about dimensional regularization, this left here, this contains a gamma 5. So when you do these computations, there is this question about gamma 5. Now people have computed these even to 2-loop accuracy. They've computed these anomalous dimensions to 3 loops. And some of these early papers really used 3 different methods of dealing with this gamma 5. So they used Tuft-Feldman, they used another scheme called naive dimensional regularization, and even a third one. They did the computations in all the schemes. They verified that at the end of the day, they got the same result. So it can sometimes be useful to do this. Also, if you, for example, use lattice gauge theory to compute this low energy matrix element, then lattice gauge theory cannot use this dimensional regularization. So you'd have to convert these Wilson coefficients into some lattice scheme or something. So the scheme is important, but also the scheme dependence must go away at the end of the day. Does that answer the question?
Yes, thank you.
Good. So there are different ways to getting these equations. One way would be to take this observable, take dd log mu, and say this has to be 0, and then this would give you some conditions. But an even nicer or more direct way is to look at the bare Wilson coefficients.
Where did you put the results?
So the bare Wilson coefficients, Ci, the ones before I renormalized the divergences, there was no mu. So I can take mu d mu. It's convenient to multiply the derivative with the mu, same as d log mu of these pair coefficients. And this has to be 0 because I don't know about the mu. And then remember that in the process of doing this renormalization, we wrote this coefficient as a renormalized coefficient. Maybe to make things easier on me, let me now write. Let me start with this. Ci, and then there was this renormalization matrix Cij. Either way, this has to be 0 as well. It's just I plugged in this renormalization condition. The coefficient here depends on mu. You see it on the blackboard that I just put down. This C factor we had yesterday. So this was the one matrix. Okay, now the matrix notation. One matrix as alpha S over 4I. Let me write. This is the final thing you'll need from yesterday. So it has the 1 over epsilon, then minus V over NC, minus V over NC, and then C. That was this matrix. This also depends on mu because it depends on alpha S, and this is the renormalized coupling, and the renormalized coupling is also a function. So this also depends on mu.
You might want to pin the board.
Yes. So let me stop this. Do you pin or do I pin? Let's see. Pin. Ah, now I also have this thing that it's backwards, but I hope for you it's forward.
For me, it's forward.
Okay. And so now we can use the product rule to evaluate this derivative. So d log mu of this. Now I'll use the vector notation, but I'm dropping this renormalization label. So I have to maybe put it here times this matrix. And then this by product rule is d log mu of the C of mu times the matrix plus the coefficient times the derivative of the matrix. And this still has to be 0. Now I multiply by from the right with an inverse of this matrix here, and you see that you can invert it. It's basically the one matrix plus a little bit. So then I get the following equation: d log mu of this coefficient C is equal to the coefficient, and then there's the product of this d log mu, the matrix times the inverse of the matrix, and this is called the anomalous dimension matrix here. So this is the equation here. And so now I have an equation that tells me the mu dependence. All I need is this anomalous dimension matrix. And this anomalous dimension matrix I can obtain by multiplying this times its inverse and taking derivatives. It turns out that there is a simple way of getting this anomalous dimension.
So when you did was multiply on the left with the
From the right with the c to the -1.
okay,
So let me put the bracket here already here. So this removes this. So then I get and maybe a minus sign. Let me check where I want to put the minus sign here. Thank you. Thanks for this. Yes, minus sign here, and then this is the large evolution. Yes, now this gamma you could plug in and go through a lot of work, but it's actually just given by twice the coefficient of the 1/epsilon pole in this matrix. So it turns out that this gamma hat is twice the coefficient of this, so it's alpha s over 4 pi, and then it's -6 over nc 6. Sorry that it's a bit together. So this is this anomalous dimension matrix. The fact that it's just given by a pole, this is special to this dimensional regularization in this MS bar scheme. This is derived in my notes, but I will not derive it here. But the quantum field theory aficionados can look up the derivation of this in the notes. So you don't have, you can directly read it off. So now we have everything. So we have this equation here. And we have the anomalous dimension.
likely think that you have alpha s that depends on mu, the beta function.
Yes, yeah. Exactly, this anomalous dimension also depends on mu through the alpha s.
Yeah, but I mean, the beta function coefficient because you take differentiate.
Exactly, you wouldn't think there's also this, you have to take the inverse matrix and multiply. It's not so clear immediately why it's so. The key is that in this MS bar scheme means you only renormalize the poles away. And since you only take the divergences away, this set has only poles. And then if you multiply this there's only poles here and only poles here. So it's very strange that then you get this finite quantity out. And so you can just sort of say, well, this is only poles, this is only poles. And now I have to take the epsilon to 0 thing here. And then you think about which combination goes with which.
Sometimes if you differentiate C, you're differentiating alpha by that is your beta function.
Exactly.
The C inverse.
Yeah. And
which
this in this.
also has the kind.
Yeah, so the C inverse, you can even forget that this order, I guess. Since it starts with a 1, so the inverse is also roughly 1. The reason that I'm not doing it is because if you take this derivative, you will need to take the derivative, the beta function in d dimensions, and so there's an extra term, and I don't want to discuss it here. But it is in these notes. So the thing is, if you compute with pair things, then so d log mu of alpha s of mu, this is equal to the beta function, and we'll use this in a minute. But on the bare level, there's an extra term, which then generates this. But it is in the notes. You can look it up and you can also ask if you want. So now I have this equation. So now I would like to solve the equation. And so the question is, can you solve this equation?
Matrix.
Oh, well, yeah, we will stare at the matrix. Heribert presumably has already exponentiated. So you would, this is of course it's a first order, the solution is some exponential, but it's an exponential on the matrix, and then one would say, you need this mu ordered exponential. I don't know whether Matt or you or both had this type of thing, but now here we're in business, it's a very simple matrix. So what you can do is do a transformation which diagonalizes this matrix, and then we'll solve the equation. It's really just exponentials. So this is the way we'll do it.
I mean, the mu dependence is in the prefect, so ordering, right? You don't have to worry about it.
Yeah, exactly. It's not,
so
yeah.
pain, there is really not much pain.
Yeah, so this is fine. So the only thing is you will have to find sort of the eigenvectors of this matrix. So now I can.
Thank you.
This is for Heribert. So which linear combinations give our eigenvalues?
Not in my head.
It's relatively simple.
Yeah,
It's
this definitely.
C plus and C minus, which is C1 plus or minus C2 are eigenvectors. And so if you go to the C plus minus basis, then you just get two decoupled equations. Log mu C plus minus is equal gamma plus minus C plus minus. This gamma plus minus alpha s over 4 pi. Basically the sum of the two entries here. I want to write here 6. Fortunately, I cannot do it in my head. That is the equation. I also call this, because we'll need it later, gamma 0 plus minus to restore the coefficient of this function. Good. So now the equation is even simpler. So let's try to solve. So by separation of variables, C plus minus over C plus minus. This is d log mu and then the gamma plus minus. And this is of course just a log of this, so exponential. Now I still want to use the following, that d alpha d log mu is beta of alpha, it's the beta function. So I can actually rewrite this d log mu as an integral over alpha s. I can write this as d alpha over beta of alpha. And of course, here I would integrate from a starting scale. Let's call this the hard scale. Maybe I could even, let's start at the large scale MW. I don't have to choose it exactly this. Do it down to scale mu. Then here, of course, it would be the alpha s at the MW to the alpha s mu. And now the gamma plus minus. Now, I've already defined the lowest order coefficient. Since we only have this at one loop order, I can also expand the beta function in minus 2 alpha s beta not alpha s over pi. And I can plug it in here. Plus the dot, but the dots are higher order, so I'll plug it in here. I'll plug the alpha s over 4 pi in here, and then I'll get minus integral s p alpha times gamma 0 plus minus over 2 times beta 0. Now I can do the integral here. So this would now be the coefficient here at the high scale, mu and w, and here I have the coefficient at the low scale. And now I have to decide where to write this. How about I remove the beta function here? So,
maybe you should explain a little bit why you're changing variables to alpha. Why this makes this, I mean, you see it if you're staring at the calculation, but I think we see this for the first time and haven't thought about this.
well, it's very nice because these are functions of alpha s already. So if I change everything to a function of alpha s, this becomes kind of nice to organize. And we'll see when we do this that we sort of get something which is very nicely organized only in powers of alpha s. So what I'm doing here is called renormalization group improved perturbation theory. You'll see that the result involves the coupling at the scale mu and the coupling at the scale mw, but you will no longer see any logs. So we have eliminated all the logs, and then in a minute I'll show you that I can plug in, let's say, the alpha s at the high or low scale, and then I'll get back the entire tower of logs. Yes.
Maybe I missed it. How was the function? How did you find how to expand the beta function?
This is sort of, I've used the textbook with my conventions. So this, so maybe often it's written like this: d alpha s d mu times mu is equal to beta of alpha s. And then, yeah, indeed, it has this minus 2 alpha s, and then there's a series of alpha s over 4 pi, and then it's beta 0 plus alpha s over 4 pi squared beta 1 plus etc. And this has been computed to 5 loops, so these coefficients are known. I can just look them up. And for us, we'll only need the lowest one. It's a bit, well, I don't know why does it have this extra factor of alpha s, because it's written in the wrong way. One should write the Archie evolution equation like this. also for alpha s, then it wouldn't have this extra factor of alpha s. So if you would have taken this factor out, then it would be d mu, d log mu of alpha s would be alpha s times an anomalous dimension. But for historical reasons, people write it in this way, then there's this extra factor. Good. So, so now I get the log. So log c plus minus equal to whatever we have here minus over 2 beta 0, and then the log alpha s mu s w. And now I can exponentiate both sides. Then I get c plus minus of mu equals c plus minus of mw times e to the minus this e to the minus this times this log, but then of course I can take this into the log, then I get this to this power, and then I get e log, so then I get alpha s of mu divided by alpha s and w to the power minus 2 gamma 0.
Too many.
Yes. Overexcited with the tools. So now you can look at this. Of course, I wiped out the results for C1 and C2, but you remember one of them had a 1 at MW and then an alpha s times minus 11 over 6. The other had a 0 and then minus alpha s over 4 pi 11 over 6. And if I choose this scale, then the logs are gone. So these now have a very nice perturbative expansion. And then I get them at the low scale, and you see there are no logs here. So I've eliminated the logs in favor of these two different couplings. And so again, this is called Archie renormalization group improved perturbation theory. And in this way, I can avoid these large logs. And avoiding is basically the same as resumming. We can, to show that we really resum these logs, I can use the result for alpha s. So if you solve the Archie evolution equation, I can of course re-express the alpha s at the low scale through the alpha s at the high scale. Some expression which you could find in the particle data group booklet or else. And the log. So I can plug this in here if you want. I mean, in principle, this is the finished result. Now this is only for pedagogical reasons. I will plug this in, and then we'll see that we sum an infinite tower of alpha times a log. So let me plug this alpha s into this formula here. So then I will get, we do the inverse here, so alpha s and w over alpha s mu times gamma 0 over 0. This cancels this, so then I get 1 plus beta 0 alpha s over 4 pi and w times log mu squared over W squared over gamma naught over 2 beta 0.
Gamma naught also had pluses and minuses in there.
Yes, exactly. Plus minus 0. Plus minus 0. Yeah. And now you can re-expand this. So this is 1 plus alpha s times a log. Of course, it's actually not really small if the log becomes large, but if you expand this out, then you get an infinite tower of such logs. So you define 1 plus, and then at the lowest order, you would get gamma 0 plus minus over 2, I guess, alpha s over 4 pi times log u squared over nw squared. And so you get an infinite power of this alpha times log. But this original expression here, this is valid as long as alpha s of mu is small. While if you stop and look at the fixed order result, this is only valid if alpha s times log is small. So now that means we have improved perturbation theory. We can now run down and compute the matrix element, avoiding any large logs. Yes, so what this here resembles, you see it's terms that go like alpha times log. So alpha s to the n log to the n. These are the leading logarithms that you have, but you can also have sub-leading logarithms where you have alpha s to the, let's say, n, and then log to the n minus 1 or so. But it's completely clear from the way we did this, we were not limited to leading order. We've done it here with the 1-loop anomalous dimension, but as I've said, people have computed this to 3-loop order. So you can also solve this equation to 3-loop order. And then you will not only resum the leading logs, but also the sub-leading logs. And this is used everywhere in flavor physics. People use this weak Hamiltonians or weak Lagrangians with this Archie improvement. There's a long review by Buras, Lauterbach, Yamin, where they present the Lagrangians for all different types of processes, and they give big matrices, etc. And I was at the summer school where Buras lectured about this, and he did all these big matrices, and I thought, what a horrible, what a horrible area of physics with all these big matrices. Let's hope I never end up working there. And 2 years later, in my first postdoc, I was working. It's not that horrible if you don't have to yourself have the matrices. Good. Maybe the last comment is there's more effective field theory to be had, and I will not get to this more effective field theory in a minute. So this modern effective field theory. So if you have this decay of a B to a D to pi minus, you can now analyze this in an effective field theory where you treat the heavy quark as very heavy. So first we made the W infinitely heavy and we removed it. Now we think of the P is still very heavy. If this P is very heavy, much heavier than the D meson, then this pion shoots off at a very high energy. So the momentum transfer is the mass difference between the two. So in the limit where you can treat this P quark as something very heavy, you get a very energetic pion flying up. And this one can analyze in this soft collinear effective theory. You would then, for this very energetic ion, you would introduce its own types of fields, called collinear fields. For the heavy quark, you would also have special field. This we'll actually do in a minute, but we'll do heavy electron instead of heavy quark. Then you have this soft stuff here. So you'll have soft stuff here and energetic stuff, which we call collinear, because it all flies into the same direction. And then one can show that these soft interactions that go from here to here, they decouple, because this is a color singlet that flies away at very high energy. So this diagram counts as this. If these two charges are very close together, it looks like color neutral. So you can actually get rid of this, and so you can factorize this process. So when you compute the amplitude for this, let me write it. Then from this drawing, if this is true, that these soft things in the B and D meson don't see the energetic pion flying away, then this factorizes off, and then you get a B to D form factor, which contains this soft non-perturbative physics. Then one gets some hard physics where you integrate out stuff going on in here times a pion light cone distribution amplitudes is similar to a PDF, but for exclusive processes. So this was one of the first applications of this soft collinear effective theory that we'll now discuss in the following. Yep. I think I've discussed everything here. The main point here was to discuss this Archie evolution equation and to show that you can use it for resummation. So here we derived this equation to all orders. So we can in principle resum these logs to arbitrary precision if we're strong enough to compute the ingredients to sufficient accuracy. So 50 minutes and we can already take a break. Maybe we can continue at 30. Is that okay? Can start. Good. So now we move to modern effective field theories. And Heribert has asked what modern is. Modern, I call those effective field theories. Okay, they're a bit younger still, even though maybe also some of them 30 years old. But the effective field theories that we considered, the low energy effective theory was just a standard quantum field theory. So for example, we integrated out the electrons and then we just wrote down the most general field theory of photons, but it was a standard field theory in some sense, up to the fact that we included higher dimensional operators. So this I would call a traditional effective field theory. This is also something where you can go to Euclidean space to formulate it. And I will consider effective field theories where you can't do this. And principally, Matt and Thomas have discussed in some sense modern effective field theories, exactly problems where there is low energy physics and high energy physics, but it's very Minkowski problems where you have special directions, etc. So examples for this type of effective field theory we already discussed: non-relativistic effective field theory, non-relativistic QED or non-relativistic QCD, or heavy quark effective theory. I've drawn a picture before where we think this B to D decay, and there one uses this heavy quark effective theory. What is special here? So the energy of the electron, this is like its mass, but the free momentum is small. This is already one of these examples, which is not like in Euclidean space, all four momentum components would be the same, but here in this non-relativistic problem, one component is very large and the other ones are small. And then the other The other example is this soft collinear effective theory. Let's see whether I can color code again. So if you look at the jet of particles, then you have very energetic particles on the one hand. This is what we had. So we had some hard probes, valence partons hitting nuclei, but then there's also soft radiation going on here. And again, not all components of the momentum scale the same here. So the energy here would be very large, but the transverse momentum would be very small. Exactly what we've been discussing all week. Again, a situation which is not very Euclidean. Maybe the other way around is that would also be interesting. And so doing this, there are certain complications. That's why I've avoided these effective theories so far. Complications. And the first complication is the thing we said, different momentum components scale in different ways. And when we did this Euler-Heisenberg-Lagrange, we did this derivative expansion to get the operators. Basically, we said, well, how many fields, how many derivatives? This, of course, gets more complicated if some components are small, but others are large, so one has to work a bit harder. So this derivative expansion is more complicated. Complicated. Then both in this non-relativistic theories and also in this soft collinear effective theory, you cannot simply integrate out particles. So you have a proton and an electron, you cannot integrate out this electron, so you cannot simply integrate particles out. But there will be some physics, will sort of be very high energy physics, which you can integrate out, while other parts have this low energy physics. And so what is done is that you split the field into what we call modes. So you would have the full theory field, and then you would split it into sort of a high energy part, which you will integrate out, and then let's say these blue parts, which would be these energetic collinear partons, and then the soft part. And so you would actually take a single QCD field, and then, so this is integrated out. Okay. So you can integrate out this high energy part, but you will need to keep these collinear partons which fly around in the jet, and you will need their soft emissions. Which is again somehow strange when you hear it the first time. How can you be that in this soft collinear effective theory? You have two different kinds of gluon fields: the soft gluon field and the collinear gluon field. The collinear one is blue, and the soft one is yellow. But of course, then can you ask, well, isn't there a double counting? How do you know what is soft and what is collinear? So there are technical complications associated with this. And the final, another complication is Blackboard is too small for all the complications. So continue with the complications in this direction, maybe. So often to construct this effective theory, you will need either to go to a specific frame. I mean, even to say what is transverse, of course, it's transverse to some direction, so you'll need reference vectors usually. So for example, when you do non-relativistic effective theory, well, the hydrogen atom is non-relativistic in its rest frame. So you will introduce some reference vector, then work with this reference vector and say, this is the vector for the rest frame of this. And in this frame, the energy is large and the momentum is small. Of course, if you would do a very hard boost, then everything would be large and you wouldn't know how to organize. So encounter these reference vectors. And the other type of reference vectors, you will also encounter reference vectors like this, and we already encountered them up to the square roots of 2. So typically in this soft collinear effective theory, you will introduce a reference vector along the direction of this jet here. So you will introduce this vector mu. This jet is very energetic, so it's approximately light-like. So you can use this thing, and then this defines, let's say, the plus component or the minus component of the momentum. It's funny that in this sketch, because this choice, the plus component is the one which has a minus minus sign. So everything is done to maximize confusion. But so once you have this, you can take the momentum component, the plus component in this direction, the minus component in the other, the transverse component is exactly what Thomas has done without using reference vectors, but we prefer to do it this way so that we can kind of write the Lagrangian in a covariant way. One can then also do things like making small changes in these reference vectors, seeing what happens, etc. There's, for example, an invariance. This n and this n bar always come together. So you can always rescale one, let's say, by a factor alpha, and the other one by a factor 1 over alpha, and the results will never change. There's also something I was reminded in the discussion this morning. What is nice when we do this type of construction, so we'll have soft and collinear gluon fields, and you can actually separately have gauge transformations on these. So we can actually really work with different gauges, let's say, for the energetic fields and for the soft fields. Don't know whether it didn't look like you needed it, but so that sometimes helps that you can choose proper gauges in those sectors. And then maybe the final complication. If you have a large energy, like the one in this jet case, let's also use some plus and minus components. If this is large, then this derivative is not suppressed. So when you start constructing operators, you can have as many derivatives as you want from this. And what this in essence gives is that certain things become non-local. Again, the Parton distribution functions are an example where this non-locality is exactly there because there's large energy along the direction. So you get operators which are more complicated than in the Euler-Heisenberg because they start to have certain specific non-localities associated with the large energy directions. Now, if we have a second week of lectures, we could try to introduce this in great detail, but I want to look at a simple example where we can see many of these features. And so I want to study soft photon emissions in electron-electron scattering. Now we get to the soft. We were discussing whether one can show that soft radiation is always classical, always given by these Wilson lines. For these QED processes, this was done by Jenny, Frauci, and Sura in a 70-page paper, which is impossible to read. And we should be able to do it in a relatively simple way using effective fields. So this is what we'll now do. Tomorrow, I'll consider jet processes. And basically, from the QED factorization theorem, it's a very small step to QCD. And then we can look at these soft emissions from jets and then develop a theory of non-global logarithms. So theory. This also matches well because we already did soft photons. These are the Heisenberg Lagrange, so it's in some sense a continuation, but now we include electrons. And say that maybe I should buy Matt some beers because he always prepares whatever I need. Unfortunately, he's not here, so no beers for him. So we'll do electron scattering. The difference to Matt's computation from the morning is I don't want to go into the small angle limit. So I'll just use the generic angle. The small angle limit is of course very interesting because then you have another small scale and you can discuss, but I don't want this. It will be generic angle scattering. And then I'll have my soft emissions here. And so this, whatever you compute in QED, you cannot just compute electron scattering. If you do it, you find infinity. It's not well defined. And this was already clear to Bloch and Nordzig in 1937 or so, before QED was even developed, because it needs basically zero energy to produce photons. Whatever you do, you'll always emit photons and you'll always have to include photons. So the cross section that we'll actually compute is E minus, going to E minus plus soft photons plus this yellow stuff. And now what we'll do is we'll use effective field theory methods to write the factorization theorem for the cross section. Of course, the experts know exactly what it is. Basically, what you see here, you will have the E plus E minus scattering. This is the hard process here with Feynman diagrams in the interior, Feynman diagrams like the ones that Matt computed in the morning. And then on top of this, you have some operator which describes this soft radiation. And secretly, this effective theory here is heavy electron theory, because the electron has the radiation here is so soft that you will never produce positrons. It's impossible. So it's just electrons moving along, radiating a little bit of soft radiation. And the Lagrangian we have, effective Lagrangian, of course, it contains this Euler-Heisenberg Lagrangian, which we constructed. So this is the one which only contains the field A mu. But for us, actually, we said these fermion loop effects are very small. So you will not really see fermion loop effects here. So we'll just use the Lagrangian. So this is the photon part of the effective Lagrangian. And now all we need is a Lagrangian for this field here, the electron field that will radiate. And to derive this Lagrangian, I want to do this diagrammatically first. By basically looking at one of these legs and then looking at the Feynman rules for this in the soft limit. So we'll just find the expansion of the diagram, and then we'll write the Lagrangian, which gives exactly the expanded Feynman rules. So I'll have my momentum P, and then I'll have here my first photon, let's say K1, second photon K2. In order not to write the sum of this P plus Q1, P plus Q2. So we have vertices here. The vertices that Matt has written yesterday and today. And then we have fermion propagators. And I will compute this diagram. And we're computing in the limit where all these photons are very soft. We start with this propagator here. So this is a fermion propagator. It has the momentum here. This is the on-shell momentum externally, and then plus some small soft stuff is floating around. And so the final rule for this is P slash plus M divided by P plus Q squared minus M squared. And now, I didn't follow my color code, so this is small. I can immediately drop this contribution. Here I have to be a little bit careful. There's a P squared which cancels the M squared, because the external one is on shell here. So I cannot immediately drop this, but then there's a 2 times P dot Q term, and then there's a Q squared term. The Q squared term again, small, I'll drop. So that means what I get is P slash plus M over 2. And we discussed that it's nice to introduce a reference vector. So I'll introduce a reference vector along the direction of this fermion here. So I will write the P here should be M times mu. It's nice, then I have these M's here and I'll have an M here, so I can do rid of certain things. And what I get is 1 plus V slash half times 1 over P dot Q. So this is this propagator after doing this expansion. In this thing here, let me call this P plus. This P plus is a projection operator, so it does something. If you square this P plus, then you will have 1 plus V slash, right, 1 plus 2 V slash plus V squared, but the P squared is equal to M squared, so the V squared is equal to 1. So I get 1 plus 2 V slash plus 1 divided by 4. So that is 2 plus 2 V slash over 4. So that is 1 plus V slash over 2. So it's a projector. If you have several of these, they boil down to a single one. And now you see you have these propagators everywhere. So the same thing that I want more. Now come the exercises. So V slash times P plus is P plus. Maybe. Yeah. Oh.
Sorry, what do the momenta P and Q actually denote?
So this is the fermion momentum. This is the electron, and this is a soft photon. So it's exactly, it's this. I want to call this Q in order only to have one momentum here, but this is of course, it's P plus K1 plus K2, and the Q2 is just the K2. So in order to write the single momentum, I'm calling it Q. But it's soft photons, 10 of them, one of them, but it's a soft momentum.
It's a different one in each of the stages, but
So I'm thinking of a long chain where I have many of these soft emissions now. And so externally, I have this fermion at the end, which is on shell. So it's momentum P mu is M times V mu, and V is a unit vector, V squared is equal to 1.
So is K1 over the Q2 minus Q1?
Exactly. So the Q1 here is this here. Q1. So by momentum conservation, Q1 is equal K1 plus K2. And the Q2 goes this way. It's maybe, I don't know whether it's, maybe it was pedagogical. I wanted to save writing one momentum, and so introduce, I'm calling these on the line, I call Q, and the ones that are emitted K.
Okay, one, okay.
Yes, everything is outgoing here. Yeah. So I have some momentum plus, and then more and more of the soft stuff gets emitted away until finally I end up with my electron in the external. And then in the computation here, I've picked one of these propagators. Let's say this one plugged in, and then this yellow momentum here is very small. So now I'm Taylor responding in the small momentum. And then I find this interesting structure here that the propagator is simpler than the full propagator. So one interesting thing, I didn't write the I epsilons, but this propagator has, for example, two poles. But now that I've expanded, I've lost one pole, so this only has a single pole. The two poles in the propagator correspond to particle and antiparticle. Now that I've expanded, I lost the antiparticle. But it's not a problem because there are no particles, antiparticles.
that should tell you, give you a hint about the dimension that projection operator projects onto. It's a projector in spin space, in spinor space. Could be, right? Particle subspace.
Yes, exactly. The original thing had the original Dirac field had 4 components, and now all of a sudden there's this projector everywhere. So 2 components get projected away. So this expansion automatically it kills the antiparticle pole, which is fine because we really expand around the particle pole. This thing is very close to its mass shell. It's just a little bit of soft radiation.
Originally was this propagator supposed to be evaluated in the final solution.
Yeah, sure.
Yeah, exactly. So there is a plus I epsilon, and there's also plus I epsilon here, and there's also plus I epsilon. And in a short while, we'll look for a Lagrangian which has this strange propagator. But I want to do the vertex first. And for the vertex, it's nice to also, I mean, this here is an external photon, so it has also some polarization vector. And if you look at this string, it's always propagator, polarization vector, propagator, polarization vector, etc. So I can squeeze this here between 2 of these. And now you can write this as a component which is along the direction of V and the transverse component. But then you find, and this is the exercise, that the transverse component vanishes and that this actually becomes epsilon dot V is plus. So somehow the propagator simplified, and also the vertices simplified. The vertices now have this epsilon dot V. In the QCD, you have QED, the vertex has a gamma mu, which is then dotted into this polarization vector. the outside. So there's the epsilon, here's the gamma mu at the vertex, times plus or minus IE, depending on your convention. And then this now becomes, instead of a gamma matrix, you just have an epsilon. Good. And now the bigger quiz question is, maybe before doing quiz questions, let me write the diagram, the result for this diagram here, and then we look for the Lagrange. So this is an outgoing electron. So at the very end here, it has a spinner U bar of P. Then it will have this, for me, it's minus IB times epsilon dot V. That is the vertex here. Then I wrote the propagator without the I, but of course it has an I as well. I over V dot, it's the Q2, it's this propagator in the Q2 plus I epsilon. And then another one here, this was the polarization epsilon 2 minus I epsilon 1 dot 3 times I over V dot Q1 plus I epsilon. And then there's this other stuff here about which we haven't talked. There is something more that's sitting there, but we have simplified the entire external leg with this very simple structure here. Good. So now the quiz is, and there's these P pluses everywhere. So there's a P plus here, a P plus here, projection operator. So now the question is, can you find a Lagrangian which gives this type of Feynman rules? I mean, we started with the QED Feynman rules, we expanded everything, and now we have a much simpler expression. Can you directly write a Lagrangian which gives this type of Feynman rules? So now again, this is a question for the quantum field theory experts. You remember what is the propagator?
It's the inverse of the differential operator. It's the vertex and everything projected onto one direction. Right. V dot Q becomes V dot D.
So yeah, exactly. So the propagator, this 1 over P squared minus M squared, this is just the inverse. This, you take the Lagrange. The Lagrangian is D'Alembert minus M squared. You Fourier transform plus M squared, and you get P squared minus M squared. You invert as the propagator. So V dot Q, that should be the differential operator in this Lagrangian. So we'll write the Lagrangian. I'll introduce some random field which I pull out of my bag. So yeah, some field somewhere, let's call it H. It's a fermion field. This is still a fermion. So it should be H bar H. Now usually you would have ID slash, but then you get 1 over P slash, which I don't want. I want V dot Q. So it's just V dot P would be the first attempt. But it's not quite right. Then we also want these interactions with the photon. And the interactions, they have a minus IE and times an epsilon. The epsilon, this will be the photon field, epsilon dot V. So the correct answer is this V dot D. And the nice thing about this, so this is H invariant. And it gives this propagator and it gives this vertex. And the other thing we want is the projection. So we can just put in one projection operator here. And then this is our differential. Yeah.
Too many H's now.
Yeah, too many H's now. Sorry, that was not your question. Say again. So if we write this out, then this V dot D is equal E, what we put it with the I, is I V dot D minus E times V dot A. And now if you want the vertex for this, take some double line is my H, and now I need the photon. Okay. So this H bar HA is just minus E times V mu. So the Feynman rule for this is we have to put the I because it's I times the action I times V mu. So this is the Feynman rule. The I from outside and then minus V mu. Usually there was a gamma mu here, then you had the gamma mu here. Now it's just replace the gamma mu by V mu and you get this Feynman rule. And then the epsilon is the polarization vector. So when you now compute diagram, I have an external photon. This has a polarization vector epsilon. And then this epsilon gets dotted into this V. So then you get V times epsilon. And again, from this I V dot T, you get V dot Q, and the inverse is the propagate. So this is what we need.
And this, so this Lagrangian that we now have, is that? Okay, so I guess the H is.
This is just some auxiliary fermion field that I've introduced. This is now really super diagrammatically. I've just said, let me find some Lagrangian. And this Lagrangian is such that it gives me exactly these expanded diagrams. And at least at the tree level, now I can get all these soft emissions correctly. And then a little bit later, I will argue that this is not changed by loops. The same Lagrangian is valid also at loop level. So this is really the Lagrangian for soft photon emission. I will rewrite it slightly. I don't want to carry this P plus along, so I'll introduce a field which I call HV, where the propagator, where this projector has already been applied. So this is this field. This already fulfills HV times P plus is HV. For V slash HV is HV. Because V slash acting on P plus gives V slash plus V squared, and V squared is 1. There is a way of getting this in the path integral by integrating out if you want. So you can, this is something Heribert already said, since this fulfills a constraint, this spinner, a projection constraint, this kills 2 components. So it is effectively a 2-component spinner, a particle spinner. And there's no anti-particles here. So this only contains 2 degrees of freedom. And then if one is to spin up and one is to spin down.
That only works
and,
if you insist on soft stuff coming out.
Yeah.
Then you don't need the other thing because you can't make it.
And you can add corrections to this, and then you'll find the Lagrangian for the hydrogen atom for the Schrödinger equation. This is the V dot V is 1, 0, 0. This is just the energy, and then you would find is equal to P squared over 2m plus other terms. So this is the first term in a non-relativistic theory. It's such an extremely non-relativistic theory that we treat this thing as having constant velocity. So nothing happens here. This electron is just walking. These photons are so soft. The electron doesn't even realize that emitted a few of these very soft guys. It just continues walking.
So I should really think of this projection as a projection to particle.
Yes,
space.
yes, yeah, yeah.
So if I operate on a U, it gives me the U back. If I operate on a V, it gives me 0.
Yeah.
So that is a use of DC generation.
Yes, yeah. Some sense, of course, you should no longer operate. We said there are no antiparticles, so it would be very mean of you now to come with a particle. This was now constructed with an antiparticle. It was constructed to describe particle spinors only.
But just somehow algebraically, if I think of it,
Yeah.
right.
Yes, yeah.
But you have picked the direction of motion.
Yes,
This is-
it's important that we have this reference vector. In order to even say what is soft, we have to go into a frame, and it's basically the frame of this particle. So this is the effective Lagrangian for the fermion field. Now, there's maybe something which is interesting and is a bit, I would say these reference vectors are maybe more useful than just picking a particular frame. Because actually we have electron scattering, so there are 4 directions.
Yeah.
I need 4 of these fields. Each one of them will sort of be sitting in its own frame. So we have 2 incoming and 2 outgoing. This is for the full one. For the 4 particles is sum I equals 1 to 4, and then for each one of them I introduce this. So I have a VI for the direction of the 2 incoming and outgoing. Then I have a VI dot V, and then in page. So that is the Lagrangian for the incoming and outgoing fermions. Plus, what is still missing in our theory is an interaction between these fermions. Deleted, no, I've not deleted, fortunately. So this is supposed to be our effective theory.
You want them to interact directly.
Sorry,
You want them to couple directly.
yes, that's all I can do basically. This there's some hard stuff here that has been computed by Matt in the morning. With some diagrams, but here this is a relatively hard momentum transfer. So these are, you should imagine, very heavy guys banging into each other and then going in other directions. So this is a hard interaction. But before they collide, they emit a bit of soft photons. They collide and then they again emit a bit of soft photons. And so I indeed write a local interaction term between the 4. Would be interesting to think whether I can also write terms where I combine 2 of these fields, but you see somehow by momentum conservation this would be very strange. A very heavy guy comes, all of a sudden it goes off into a different direction. So this you cannot write, it doesn't work. But I can put 4 of these together, and I'll do it in a primitive way. You could now think long and hard about what Dirac structures you want to put there or not. That this I will not do. I will simply take 4 indices, alpha, beta, gamma, delta. Then, of course, this scattering amplitude, this will depend on the 4 velocities of the particles. So I'll use this. This is V1, V2, V3, V4. And then, of course, it depends on the center of mass energy comes in here. And this is the only dependence. The scattering also depends on the angles, but if you have these directions fixed and if you have the energy, you can compute the angle. So this is it. And then I have 4 fields, 2 outgoing ones. Let's call this 3 and 4. Gamma, H bar, V4, delta. then H V1 alpha, H V2 beta. These are Dirac indices. So that is the operator. And of course, it's somehow many operators or many Wilson coefficients, and it's not very elegant. Everything has to be a scalar, so I could, but we can just leave it like this. So that is good enough. That is the most general interaction term, unless I would put more fields or I would put derivatives or something, and this I don't want to do. I only want the leading one. If I would put additional derivatives, that would be additional small soft momenta, so this would be power suppressed.
These are just external scale and introduce the volume, the V and the E.
No, these are the. So I have here 4 momentum in these scattering processes: V1, V2, V3, V4. I write each of them. EI is equal to mass times VI. So maybe even instead of center of mass energy, I can just write electron mass here even better. So these are the 4 momenta in this scattering. I replace them by 4 velocities and 1-dimensional full quantity, for example, the electrons. And so this is now a function of this. If you compute Will's 2 diagrams, then you get some results which he had, where you get P1 minus P2 squared or something. It's more like a T channel, P1 minus P3 squared. That is the same as M squared times V1, V3, etc. So you can express all the invariants in the scattering through these velocities and the mass. And so that's, now you have the effective theory. It's a free Lagrangian for photons, plus these kinetic terms for these non-relativistic fermions, plus an interaction term like this. So now the next thing we should do is to do the matching. And it's maybe, in some sense, this is almost what we discussed now. So how can I determine this coefficient C, alpha, beta, gamma, whatnot? So to do it, we have to do the computation of this scattering first in QED and then in the effective theory. And this Wilson coefficient, this is now good for any process you want. So this I will compute without soft photons. So this is one diagram. This is the other diagram. So these are the QED diagrams computed this morning. And then I have to do the computation in the effective theory. It's especially simple if I don't compute the scattering amplitude, but this amputated Green's function, where I take these propagators here away so that I have alpha, beta, gamma, delta as indices. In effective theory, it's really just this diagram here, where this is this coefficient. Or, yeah, so in effective theory, this is just the C alpha, delta, gamma, delta, depending on the velocities. So this coefficient is nothing but the scattering amplitude, which in some sense also it makes sense. A hard process is really the scattering thing without these spin indices which are contracted with this. So it's Dirac indices which are contracted. So what you really would do if you compute the scattering amplitude, you would of course get external spinners for these 4 things. So if you compute this, so this is 1, 2, 3, 4. So you get U are 3 of m times v3. So we'll get the spinner for this outgoing, spinner for the other outgoing with the index gamma. Then
I want to think of this as matrices, C alpha beta gamma, that is kind of a end of product of Dirac gamma matrices.
exactly, so that the elegant way would be to introduce the basis of Dirac matrices and then write everything as scalars. So that's how the professionals would do it, but it's somehow lost work because anyhow this thing is just a scattering amplitude. So rather than putting it in tensor structures, I can just leave it as this. So this is the delta, and then a u times m v1 alpha u m v2. So the funny thing is this scattering amplitude is now modulo the spinners is just a Wilson coefficient now. And this is now for the professionals like Heribert, if you do this matching at the one loop level, and if you don't include soft photons, there is a divergence here. However, here all the loop diagrams are scaleless, so you have 1 over epsilon ultraviolet minus 1 over epsilon infrared. So at the one loop level, there will be an anomalous dimension of this Wilson coefficient, but it corresponds to the infrared divergence of this hard process. So that's how it works. So this is actually a fun thing to do, that in this way of doing effective field theory amplitudes, their ultraviolet divergences correspond to the infrared divergences of the full theory. And we did this with QCD amplitudes, and we can derive the structure of infrared divergences in QCD at 3 and 4 loop level using these techniques. So this is not only true in the soft effective theory, but if you have massless particles, you could do the same.
This reminds me of what happened, I understand correctly, finite temperature.
It's
and then somehow you have.
It's something that you can always say that the infrared end of the high energy stuff has matched the ultraviolet end of the other one. That's how these two things go together. Good. 10 minutes. Let me look at the audience, how tired or not tired you are. Maybe we can, if you're strong enough, we can do the factorization theorem now. Because you feel very well prepared. So we matched, we know what this is, but even do it at the loop level and get this Wilson coefficient. And we have this effective Lagrange. If you remember this, then I can wipe it away. And now I'll introduce, now we come to the crucial point, I'll introduce the Wilson line out of nowhere. I'll call this the Wilson line SI. And for the incoming particles, it's an integral from -infinity 0. So you should, I didn't explain at all why I introduced this Wilson line, but we've kind of encountered, maybe you call them iconals, but it's the same thing. So iconal phase. So I'll just introduce this without explaining why. The integral from -infinity to 0, and then the velocity vector vi times ax plus s.
You don't see a pulse ordering because this is electrodynamics. And
yes, exactly. It's now easier. We'll do tomorrow the same in QCD. Then we'll have a path order because there's a matrix, color matrix in the exponent. Here it's just the iconal phase is the right way. So this
only going to 0.
Yeah, why I'm integrating, what I really do is I start at -infinity with this S, and then I run to the point X. So there is a point X here. This will be the point where these fermions collide. And then I start at -infinity and I integrate along this way until I hit the point 0.
But the difference to my, two differences to my Wilson line is times to 0, whereas I was no longer part of the cluster community.
Yes, so this is for the incoming ones. For the outgoing ones, I would want the same, but I'll integrate from 0 to infinity. So
And the other difference is that I guess here the A is a quantum field,
yes, it's really a quantum field operator with everything.
Also, so I'm more interested in absorbing photons from classical field. You are emitting photons from
Yeah, so
this is an actual field operator of a classical field.
Yeah, it's really a quantum field, etc. with the full. But except, so I haven't motivated this. The reason that I like this Wilson line is that it fulfills a nice equation. If you have V dot V acting on this Wilson line Si of X, then you get 0. Or if you have some other function sitting here, then you get Si of X times the V dot regular derivative of this function.
And it's VI.
VI, exactly. So this Wilson line sort of parallel transports along this way, and then the covariant derivative along this transport direction is 0, or if you have a product here, it becomes an alternate. So that's a nice property of this Wilson line. And now we do a field redefinition. You see my Lagrangian here. I redefine the HVI of X as this Wilson line Si of X. So this will now be the crucial step, times a new field, VI, and I'll call this field 0, not because it's bare, but because it will be non-interactive. That is just some phase factor. So this is a possible field redefinition. We've already used field redefinitions, so it's a unitary field redefinition. So it's a very nice one. Should be a Jacobian or something. So now I can plug this into the Lagrangian. So this, let me just take one copy of this. Say, I will not write the I, but now we'll just use one velocity. H bar V I V V dot H V. I'll plug this in. Then I'll get H bar 0. The bar is the dagger of this, so I'll get an S dagger of V, then an I V dot D S V, and H0. Now we use this relation that the derivative along the line is 0 or only acts on the function here. And so that means I can pull this here to the other side. Then I get SS dagger, and my dipole is at the same point. So this is just 1. Cancels here. So I get H bar 0 V I V dot regular derivative. So no longer any photon interaction times H V. Fantastic. So we've decoupled the soft photons from this Lagrangian. So
I gather the H0 already has like multiple emissions.
no emissions any longer. It's just the regular derivative. This thing doesn't interact. So now it's a fermion that no longer interacts.
It's kind of rest electron.
Yes, so of course, what exactly the quiz question is, where did the Wilson lines go now? Did we completely get rid of soft photons? That would be wrong. So where are these? It's not true that this is completely gone. So where are the Wilson lines now?
Are there any other places where H appears?
Yeah, are there other places where H appears and where these do not completely decouple?
Just the usual. Sneaky guy. He is.
in the interaction Lagrange, sort of what happens is they cancel in the kinetic term, so you get fermion fields which no longer emit photons, but they now appear in the interaction. So the delta L interaction. This is still our C alpha beta gamma delta. Then there are these fields which do not interact. Let me just write 3 and 4 instead of always these H1 0, H2 0. All of these are getting redefined. They are alpha, gamma, delta, alpha, beta, contracted with this. But then each one of those get a Wilson line. So now I have S dagger E3, S dagger E4, S31, S32. And these don't cancel because it's different directions. So now the nice thing. If we compute the amplitude for E plus C minus, for E plus, sorry, E minus, E minus, E minus, E minus, plus any amount of photons, I can now use this effective Lagrangian here. And I have these 3 fermions, they don't do anything. So you really just get this U bar 3, U bar, V3. Can I just write 3 and 4? It's U bar of M times V3. But it's U bar 3, U bar 4, U1, U2, gamma, delta, alpha, beta times C, alpha, beta, gamma, delta. And then I have these Wilson lines and the soft photon. So there's a matrix element where I have 10,000 soft photons sitting in the final state, and then SV1, V3 dagger, SV4 dagger, SV1, SV2. And this, we said we know what it is. It's just the amplitude without the photons. So this entire thing is the amplitude for E plus E minus, E minus scattering times the soft matrix element.
You have there's an amplitude, there's E plus, E minus, and then you can emit 1 photon, you can emit 2 soft photons.
0 soft photons. This is the amplitude with 0 soft photons computed at N loop level. This is the matrix element with soft photons.
Yeah, but not
computed
total,
at the N level again.
Sorry, the total thing that we have.
Yeah, the total thing is E minus to E minus plus many soft photons. But now I've factorized it into a product. And so this is, it should now celebrate. We have a matrix, a low energy matrix element, and we have a high energy matrix element. And if I write the cross section now, it will be the last thing that I'll write. So if I have the cross section, sigma, this is now given by a hard function. A hard function is the square of this electron-electron scattering with phase space and 1/2s. It depends on these velocity vectors and the electron mass times the matrix element squared for the soft stuff with a constraint, for example, saying that the total soft energy has to be smaller than something or so. So times the soft function depending on the maximum amount of soft energy to allow. So this is kind of a remarkable result. We've managed to show that this amplitude with the many soft photons factorizes into, or the cross section factorizes into a function without any soft photons times a soft function. These functions might have divergences, but we can renormalize this hard function and we can renormalize this Wilson line matrix element. And so then we have separated these two things. This is the hard scale, this is the soft scale. We can use renormalization group techniques again to do this resonation. And this is now for a collider.
So you can see easy enough how to calculate the hard part.
The soft is also not so difficult. The soft is these Wilson lines, and these Wilson lines have actually the same Feynman rules as our original Lagrangian, basically. So if you want to compute the soft function, I use this double line for this Wilson line. So this is E1, E2, E3, E4. And now you take the soft dimension here and go from one leg to another. So we compute things like this. So this is here, this XS is just one soft photon, or you can do things with 5 photons. You can
I mean, for QED, you probably can do the whole thing.
Yes, so the nice thing about QED is that these Wilson lines have some amazing property that if you compute this one loop diagram, you can just exponentiate it and you have the all order result. This is a special, this will not be true in QED, it's really that simple. And then the last thing which I have to discuss tomorrow is all our derivation was, of course, based on expanding 3-level diagrams. And so you could ask questions, well, was this good enough or not? But what I want to discuss is that there's a method called method of regions where you expand loop diagrams. And in fact, the method consists of doing exactly the expansions we did. So this result is not only valid at 3-level, but also at 17 loop order. And also because this thing exponentiates, which maybe we can discuss tomorrow, that means that the infrared divergences of 17 loop diagrams in QED somehow also have to exponentiate and have exactly this structure that is predicted.
So this maybe for the tutorial you can explain some stuff to me about. I'm trying to read through this old Koshemsky paper, and I feel like
Koshemsky is of course the master of these Wilson lines. Yes. I should also in this book that in my book on the soft collinear effective theory, there's about 2 or 3 appendices on Wilson lines. For example, here I've simply used this fact that V dot E of S is 0. One can even, this is really one of the defining properties. You could even define the entire Wilson line as saying V dot D of some object has to be 0 and the object has to be 1 if the thing is, then you can integrate, then you automatically get it. But one can show this all by expanding and by applying the limit. This could be good.
Right, so let's take a break. For how long?
Fantastic.